Have you ever stopped to wonder how your computer, your phone, or even just your calculator actually makes a decision? I mean, it seems like pure magic, right? But underneath all that incredible complexity, there's a secret language, and it's made of unbelievably simple rules. So let's dive in and decode that language together.
It really all boils down to this one fundamental question. Everything a computer does is based on just two states: on, which we represent as a 1, and off, which we call a 0. So how in the world do you get from simple electricity to complex thought?
Well, the answer lies in these brilliant little devices that act as the gatekeepers of information. They are the absolute bedrock, the fundamental building blocks that let machines follow rules and, well, think.
And here it is, our core definition. A logic gate is basically a tiny decision maker. It takes in one or more electrical signals, our ones and zeros, and it spits out a single new signal based on a very, very specific rule.
All right, so let's meet the team. We're going to start with the 3 most fundamental gates out there. If you can master these, you've pretty much mastered the basics of how every single digital circuit works.
First up, we've got the simplest one of all, the NOT gate. Its job is incredibly straightforward. You could call it the ultimate rebel. Whatever you give it, it gives you back the exact opposite, which is why it's also called an inverter.
Let's see how this works. It's super simple. The truth table over on the right shows you every single possibility. If the input A is 0, the output X is 1. If the input is 1, the output is 0. See? It's a perfect flip every single time.
Next up, we have the AND gate. Now, unlike the simple NOT gate, this one takes 2 inputs. I like to call it the perfectionist, and that's because it has really high standards. It demands that every single one of its conditions is met before it'll give you a positive result.
And this right here shows you its strict nature perfectly. Take a look at that truth table. There is only one single scenario where the output X is a 1, and that's when input A and input B are both 1. In every other case, if even just one of those inputs is a 0, the output is 0, no exceptions.
Now, in complete contrast to our perfectionist AND gate, we have the OR gate. This one is way more easygoing. It's happy to give you a positive result if just one of its conditions is met. It's the accommodator.
And you can see just how lenient it is in its truth table. The only way you're ever going to get a 0 out of this thing is if input A and input B are both 0. If either A or B, or hey, even both of them, are a 1, the output is going to be a 1. It's a lot more forgiving.
Okay, so now that we've got our 3 basic decision makers down, let's see what happens when we start to tweak them a little bit. By combining or slightly changing these basic gates, we can create all sorts of new, more specialized rules.
So, meet the XOR gate. XOR stands for exclusive OR. It's a lot like our friendly OR gate, but it has one very important exclusive condition. Think of it as the you can have cake or ice cream, but not both gate.
And this comparison is just perfect. On the left, you've got our regular OR gate. On the right, the XOR gate. They look totally identical until you get to that very last row. When both inputs are 1, the OR gate says, sure, that's a 1. But the XOR gate says, nope, sorry, that's a 0. It's exclusively one or the other.
So what happens when we combine our basic gates with that simple little NOT gate? Well, we get their opposites. A NAND gate is just a NOT AND. A NOR gate is a NOT OR. It really is that straightforward.
And here's a great little visual trick for you. See that small circle at the tip of the NAND and NOR gate symbols? That's the universal sign for invert. It's like having a tiny NOT gate stuck right on the end, just flipping the final result.
So, these individual gates are pretty neat on their own, but their true power is unleashed when we start connecting them together. This is how we go from making simple yes or no decisions to performing really complex calculations.
And this is where things get really powerful. In this diagram, we're not just using one gate, we're chaining them together. You see how the output from that top AND gate doesn't just stop? It becomes a brand new input for that final OR gate. This is how we start building a more complex question out of simpler ones.
Okay, let's actually trace one of these paths together. Look at the second to last row where A is 1, B is 1, and C is 0. Okay? So the top AND gate gets a 1 and a 1, so its output D is a 1. The bottom AND gate gets a 1 and a 0, so its output E has to be 0. And finally, the OR gate gets that 1 from D and that 0 from E. Since one of its inputs is 1, the final output X is 1. See? Perfect. And this specific circuit, it's called a multiplexer, and it's super fundamental for helping a computer choose which data to pay attention to. You chain just a few more of these together, and you're building a circuit that can actually add numbers.
Okay, let's zoom out from the diagrams for a second. Why does any of this actually matter? Well, because billions of these tiny decision makers are working together right now inside the very device you're watching this on.
So, what's the big takeaway here? It's that every single digital device you have ever used in your life is built from these fundamental logic gates. Your computer's processor, your calculator, the control systems inside a car, it's all just countless and, or, and not gates, all combined in incredibly clever ways.
And that just leaves us with a final thought to chew on. We have built our entire technological world on a foundation of simple yes or no questions, just asked at lightning speed over and over again. It kind of makes you wonder, what are we going to build with them next?